So today I know that this is ELCE, so which is supposed to be most embedded Linux, but I'm going to give you a talk about Android. So today we are going to discover what is the networking and the connectivity layers in Android, and how we, in my company at least, managed to add the support for the Ethernet connectivity, which is not something that comes out of the box with Android. So just a little slide about me. So I'm working as the Android platform architect for my company for like a year or a year and a half now. I've been doing a lot of open source software and working on embedded system designs for like almost 10 years now. Mostly involved in DSP integrations and low-level drivers development, this kind of stuff. I'm also a regular contributor for open source projects. So the most significant projects that I've been working on are the OpenBricks and the Geeksbox projects, which I led, which are embedded Linux distribution or cross-distribution builder, like the build root project or an embedded. And I've also been involved a lot in multimedia area with the uShare UPnP development, media server development, and the player media player development. I've also been a recurrent speaker to various conferences and events from the Linux Foundations for the last 3 years. Mostly involved in ELCE, ELCE, and Android Build Summit. If you're going to have more information, or if you want really to have more information about Android, I can only recommend 2 excellent books. One is from Karen Yagmur, which is back in the room. This is really if you really want to know how Android works in the embedded layers, or you want to build your own, as a manufacturer, if you want to build your own device, this is an excellent book to read. It's probably going to be out by next year. On the other hand, if you're more interested in the software architecture of Android or how to develop applications and how the different building blocks actually work together, I can only recommend the Learning Android book from Marco Garganta. It's a really good book. Following that, I've also been doing my own publications. So I've been writing some articles in a French magazine, which is GNU Linux magazine in France. So for non-French speakers, maybe they're going to be translated in English someday, but it covers many different aspects of how to build your own device for Android. So, a bit more information about my work context and how we came with the idea of adding Ethernet support in Android. So, what we are doing in my company is designing an enterprise desktop IP phone. So this is the kind of product that I'm speaking about. It really differs from the usual Android devices that you may find. Mostly because it's not a smartphone. So what I mean by that is that the device is always connected. He has no battery, he has no radio, so no baseband processor, no GSM, CDMA, whatever. It's always docked, he has no screen rotations, no accelerometer, no GPS. So it's really not the usual kind of Android device that you may find. So it's really not a smartphone, so that's really a crucial point. And what we have instead is this kind of IP phone as Wi-Fi support, but only as not in station mode, only in access point mode. So this is also something a bit different from the smartphone platforms that you may find. And most of all, it has its main connectivity layer comes from the LAN, because it has an integrated Ethernet switch. So we'll see what it means about adding this kind of support in Android. So this slide is really meaningful to me because if I've been working as a brain for the development and the architecturing of all the devices that we have made about these connectivity layers, this is the man of my team who has done the job, so he gets his head dirty, and I really want to thank this guy for that. He couldn't be here on today, but at least he's on the slide. What you have to know before going further in the connectivity layers is that Android really differs from the usual Linux distribution that you may find. So one important thing to know is that Android supports different kinds of network interfaces. It supports obviously the mobile interface because it's meant for phones, so you have 3G interface for data. It can also support Bluetooth, Wi-Fi, WiMAX, and at least in the API, it even supports Ethernet. But it doesn't come out of the box. One thing that you have to know is that Android only supports one network interface at a time. So data can only come from one side. So if it comes from 3G, it just doesn't care about the other interface. If it comes from Wi-Fi, the other ones, we just do not care. So different kind of interfaces are supported, and there is one key element in Android in the system layer, which is called the connectivity manager. So the connectivity manager is one Java service which is really specific to Android. It acts like the network manager that you may find in the Linux distribution with GNOME and with a bit with Command, but it's really specific to Android. And it's really a key point for all the connectivity in Android, and it really understands and deals with all different kinds of interfaces that you may find. So one of the interfaces that we support is the radio layer, so it's obviously for mobile phones. So the radio layer interface, which is also called REAL, it's used to communicate with the broadband processor, and it's used to give both voice, because it's a phone, but also for data. If you want to have data through your 3G plan, something like that, it comes from the same place. So in Android, you get a basement processor, and you get the Linux kernel, which has all the drivers with the regular Linux IP stack, and the packet driver that handles all the data connections. On top of that, you get some HAL, which is really proprietary implementation by the different SoC vendor and basement processor vendors, which does something obscure in a black box way and interface with this basement processor to provide data to your system. On top of that, you get the different application frameworks and the different applications which are really Java-based and which deal with the real layers for a unique interface. But once this interface is connected and once data are available, the connectivity, what you have to know is that the connectivity manager exports the data through one type, which is called type mobile. There are actually different types of mobile extensions depending on the 3G or 4G layers, the kind of connectivity that you have. And the kind of interface that is available in Android is the Bluetooth interface. So the Bluetooth interface, once again, comes with a Bluetooth chipset at the low-level hardware level. The Bluetooth chipset is driven by the Linux kernel, and on top of that, you get the BlueZ stack. So the BlueZ stack is the major stack that you can find in the GNU Linux distribution, and is also used in Android. What it does is providing all the different Bluetooth profile supports, and the Android framework interacts with the BlueZ stack through the dbus mechanism. So Android has its own, I would say, IPC mechanism, which is called binder, and even with that, it includes dbus for the only reason of communicating with the BlueZ stack. The reason is because BlueZ is GPL, and Android just does not want to care with GPL licenses and real open source software. So it just uses dbus to interact with that. What you have to know is that as for the mobile application, all the application, all the Java framework is just written in Java, and it uses the interface to the BlueZ stack and to another stack which is called the libBlueDroid to interact with the low level. And once connected, this is exported by the connectivity manager through one type, which is called the type Bluetooth, obviously. Bluetooth is also used or also interfaced with another program which is called netd, which is another really important system daemon that exists in Android, which is an abbreviation for network daemon, obviously. This is like a connectivity manager, which is the top-level interface for Java applications. netd is actually the low-level implementation of all network transactions. So netd is one daemon that is actually responsible for tethering, for example. So if you want to route packets from one interface to the other, acting like an access point, or for example, if you have data coming from the 3G network, you want to forward them to Wi-Fi or through USB to your PC, this kind of stuff. This is done by netd. So this netd daemon is actually one implemented in C, and it uses a Unix socket, and all the applications can connect to the socket and just ask netd to forward data from one interface to the other. What does netd actually is using IP tables. It also uses DNS masquerading. So really, if you want to create some kind of access points, this is where the intelligence comes from. Another kind of network interface that is supported is the NFC interface. So NFC stands for Near Field Communications. I don't know if everybody here is aware of that, but it's something, it's kind of new chips that have been integrated in Android with ice cream sandwich, and it's available on the recent smartphones. So it's some kind of local proximity chip. By local, I mean 3 to 5 centimeters. And you can, it's working like the RFID technology. So if you just take your smartphone and you come close to another smartphone, it can exchange data between the smartphone, or if you have some passive RFID tags in museums, this kind of stuff, you can just take the smartphone and read the data from that. So this is also one kind of network interface. It was not planned in Android at first, so it's used to exchange data, but it's not interfacing with the connectivity service or connectivity manager right now. So it's a bit different, but still, as usual with Android, you find some NFC chipset and some low-level NFC drivers that is implemented in the Linux kernel. And on top of that, you find some HAL, which is used by the user space and the Java framework to actually interface with the low-level drivers. Interestingly, if you ever look at the NFC HAL, you will see that it's not really generic. So it's not really a HAL, because normally it should be hardware independent. And if you have a look at this, you see that only the chips from NXP and the PM544 are actually supported right now. So it's a HAL, but only for one device, so not really that good. At least what you need to know is that this NFC interface is not connected to the connectivity service and manager. The other kind of network interface that is really important and really used in Android is the Wi-Fi, obviously. So the Wi-Fi in Android can work in different modes. So the mode that you may find the most used is the station mode. So you have one access point and your smartphone just connect to the access point. It can also work as a peer-to-peer interface. So if you just want to have two smartphones and exchange data, this is possible. And it can also work as an access point. And as said earlier, it's provided by the netd daemon. So this is some diagram of the complex software architecture that you may find in Android. So what you need to understand over that is all the Java applications, so really on top of the diagram, they connect to the connectivity service and the connectivity manager. Every time they want to know something about the network, am I connected or not, which way am I connected, they need to ask the connectivity service and the connectivity manager for what is the given state of the network and the connectivity. So on bottom of that, the connectivity manager supports different kind of other managers. So usually here you have a Wi-Fi manager, you also have a Wi-Fi peer-to-peer manager, and for the different other kind of interface, you find the same kind of manager. So each network interface has one manager, and all these managers are gathered into one, which is the connectivity manager. And it's this one which has full control of the connectivity state of Android. So as for Wi-Fi, it's a bit complicated as usual with Android, but you find many Java classes which are related to providing the service and to providing state machine because Wi-Fi is really complicated, so they have to implement a state machine saying, okay, am I connected? Am I losing connection? Am I actually working as a station? Am I working as an access point? This kind of stuff. So this is inner classes that deals with Wi-Fi, and they also deals with all the Wi-Fi configuration and peer-to-peer configuration, because for Wi-Fi, as you have the passphrase and the WEP or the WPA authentication, then you need to store this kind of information somewhere. So this is stored in the secure and system settings, which is some hidden database that are restricted to the system. This is really for configuration, but if you want to deal with the Wi-Fi from I would say from a control perspective, then you have one class which is really important, which is the Wi-Fi net native. And the Wi-Fi native is actually one class that does, like many times in Android, GNI connection to the lowest level. So this GNI connection is meant to bind the Java world to the C or C++ world. So this is done by the HAL, which is implemented in the lib hardware legacy library, and also in the WPA supplicant applications and extensions, which are really used to control the Wi-Fi. So, and below that, you may find also something that really differs from Linux to Android, which is called the libnetutils. So the libnetutils is some library that does many, I would say provide many helpers for bringing connectivity and bringing interfaces up or down, or configuring interfaces, or configuring the network routes and this kind of stuff. So this is implemented in some specific library that is, once again, specific to Android. And Android provides different, I would say, usual utilities like ifconfig or routes on this kind of stuff. But if the behavior is, if the name is generic and the behavior is also expected, it's actually using custom Android implementation. One interesting thing to know also is that the libnetutils provides some DHCP implementation, and Android also has another implementation, which is the DHCP client daemon. So there is actually at least 2 implementations of the DHCP client in Android. So my guess is that 2 different teams at Google were working on different parts, and they implemented the wheel twice, but it's really buggy. And this is really important because we'll see with Ethernet that the implementation is different, and they do not use the same DHCP stack. Why this is important is because mostly when you are in big corporations, you may have to hack around DHCP because you want to add some specific vendor options or this kind of stuff. And knowing that, you have to know that you have to do that here, but also here. So 2 kinds of implementation and 2 kinds of hack, depending on whether you are using Ethernet or whether you are using Wi-Fi for DHCP. I know, for example, that in my company, I have to hack the DHCP implementation to say, okay, I am a Windows PC, otherwise the DHCP server doesn't provide me an IP address. This is stupid, but this is some big corporation works this way. So. And the connectivity manager for that, at least, it provides, it tells the application that yes, the data are available and they are connected through the tight Wi-Fi. So, no, if you want to focus more on the Ethernet, which is why you came here, you have to know that Ethernet is supposed to be supported by Android. By supposed to, I mean that in the API they have, at the connectivity manager level, they have a lot of defines about the different supported network interfaces, and Ethernet is in there. In reality, it's not completely the case. So we'll see why. So Ethernet is supported through the native Linux kernel drivers. That's kind of obvious. If you go in a shell, so just log in with ADB, you hit ifconfig, netconfig, or ping commands, they work. So it's really easy, you can configure your interface. Due to Android using Bionic, the DNS implementation is a bit different. So in Android you do not have etc result.conf file. So if you want to ping, you have to do something else. You can't just put your name server in this kind of file. It doesn't work. If you have other kind of native system daemons which are written in C and C++, they work out of the box in Android because they use the regular Linux networking API using POSIX sockets, and they work. There is no problem with that. The problem is that the Java applications, they do not work. So we have a gap between the two, and we have to understand why the low-level applications fully support Ethernet, but the Java applications, they have no idea about. So this is done once again in the connectivity manager. All the Java services and all the Java applications, they ask for the connectivity manager. They say, okay, do you have some data interface? Is it available? And Android just say, it's not available. I have no 3G, I have no Wi-Fi, so I don't have any connection. And so the application just stops. They do not even try to do some connectivity because they do not know about Ethernet. Some applications still work. So if you had the chance, I can say if it's a chance or not, but if you had the chance to try some Chinese tablets, sometimes you may find some Ethernet port on the tablet. And if you plug it in, you may get some IP address through DHCP, and the browser may work. So, but the other applications, they just do not. So the browser works, but it's more a side effect because the browser is actually using WebKit, which is implemented in C and C++, and just doesn't care about the connectivity manager and everything. And it's Linux application, so it works. But for the real Java Android applications, it doesn't work. So what we have to do there is create this kind of Ethernet connectivity manager, like it's the case for Wi-Fi, and connect it to the connectivity manager. So this is even more difficult when you consider the enterprise requirements, which are a bit more complicated than just the average consumer requirements. Because in enterprise, you have the reliability is really one key point. So you have to ensure that the data connection works in 100% cases. You just can say, okay, this application works and this may or may not, or sometimes it may. It has to work every time in all possible cases. Also, one thing that you have in most of the big corporations is a proxy, HTTP proxy. So this is also something that Android is not completely supposed to handle, because once again it's meant for mobile and tablets, so it just connects through home, through your personal Wi-Fi or through your 3G network. HTTP proxy is not really supported. Also in big corporations you have firewalls, which may prevent some applications to work or some ports may be blocked. And sometimes you may also require some 802.1x authentication over Ethernet. So that's the kind of requirements that we have. And fortunately, there is some patch that exists that implements the Ethernet Connectivity Manager. So the name is called ECM. And this ECM patch is something non-official, so it's not at all supported by Google, but it has been brought by the Android x86 team. So when Android has been ported to the x86, mostly for the netbooks, all the people here say, okay, I have some Ethernet, I want to be able to use it. So they made some development about this ECM, but the implementation is not completely 100% accurate. So this implementation is not included in Google official AOSP tree, but it has been included in the line hour tree. And I've been told yesterday that it's also been integrated in the TI robots tree. Still, it's not completely accurate, and you can't just use it this way. So what we did in my company was to take this patch and modify it for meeting the different enterprise requirements that we have. So if we have a look at this patch, the implementation is pretty much the same than for the Wi-Fi, to the exception that it's pretty much upside down. So all of the different state machine and Ethernet information and the GNI layers, they are implemented behind the connectivity service and not below the Ethernet manager. But it's really some implementation details. So the implementation mismatched bits from the Wi-Fi implementation, and it's written on the other side. It's on the wrong side of the slide, but it doesn't rely. It relies on DHCPD instead of libnetutils, which is called by the Wi-Fi. So as I said, there are two different implementations, two different DHCP, and they do not use the same. So the behavior may change. So if you apply this patch, you may see some changes in the Android framework. So, for example, if you go in the settings applications, you now have some new menu that allows you to configure your Ethernet device. So it lists all the network interface that you have, and it allows you to provide to connect to DHCP or providing a static IP address. So by default, the ECM patch, it supports DHCP implementation. From the menu, it provides the static IP address. In the facts, it's not implemented. So we have to do some changes about that just to support putting some IP address in the user interface and ensuring that everything is done and tuned up to the load. It also, in the system UI applications, it also adds some new information. So here you can say that Ethernet is connected. So the patch really works. So to this patch, we actually, if you just take it from the Android x86 mailing list, you may have to do many modifications. So I'm going to list this modification that we have done, but one of the things is that this patch misses one thing, which is registering the Ethernet service. So they have implemented the service, but they do not register it to the framework. So Android has no chance of knowing that the service actually exists, and the application has no chance of actually being able to call it. So this is some example code, but if you want to have a look later on the slides, they will be published in SlideShare, so you may just, if you're interested in that, you may just pick the code and put it in your own implementation. So one thing that we have to do is register the Ethernet service, and the other thing that we had to do was to modify the connectivity service, and just adding these two lines saying, letting the connectivity service that Ethernet actually exists. So it's a simple two lines of code, but all the application, when they just asked the connectivity service, am I connected? Through the Ethernet, the connectivity service just doesn't answer. So with these two lines, it just answers. What we have changed also is the connectivity manager. This may not be the case for everyone, but as I said, in our case, the Ethernet is the main configuration point, so we just have to tell Android in the connectivity manager that the default network preference is the Ethernet and not the Wi-Fi anymore. If you do that, then you may also have to update the APIs because it changes quite a bit. What we also have done is modify the Ethernet service that came from this ECM patch to always say, okay, ETH0 is my default interface. This is because, once again, Android doesn't support multiple interfaces, so you can't have two Wi-Fi interfaces, you can't have two Ethernet interfaces, and by default, it just tries to list all the network interface that you have, so you may find localhost or the IPv6 tunnel. So by default, we just want to ensure that ETH0 is the default interface, so we just have hard-coded this way. So at this point, the Ethernet was, I would say, kind of working. So we were able to plug the network cable. The DHCP brings up some IP address. Okay, it seems to ping. We have some routes. We can go out. We can go in. Okay, it seems to work. But it's not working in all applications. So we will see that now we have tried many use cases and we will want to have it really functional in every cases. So one thing that we have done first is, okay, you are connected to Ethernet. This is important. Yes?
Yeah, the patch that you spoke about, it's already part of Android, or it's your private patch that you need to?
It's not provided in Android. So you have to take the patch from the Android x86 team and then bring all the modifications that we have made. All the modifications that we have made will, however, be open sourced. so including the original patch plus all the modifications. So I have not yet published them because it's not in the best shape right now, but the goal is to open source everything.
And change the DNS as is today, it doesn't support the SMS at all?
No, not at all. So what we have done first is that, okay, Ethernet is connected, and you can see that if you ADB shell to your system. But for the user perspective, it's kind of interesting to know what is the MAC address, what is the IP address, this kind of thing. So we have made some modification in the settings application for the status menu, just in order to provide these two strings with the Ethernet IP address and the MAC address, the same way that it is done for the Wi-Fi. So once again, the code is not really important, but if you want to have a look later, it's up there. What we have done is just modifying the settings interface to declare a new field with the Ethernet IP address. And then in the Java code, we have just made some requests to the Ethernet manager and the Ethernet service, and saying, okay, I want to get the IP address and I want to put it in that string. So it's really kind of easy. It's really regular Android applications that I would say. For the MAC address, it goes the same. We just create some new field, and in the Java layer, we just ask something. The only thing that we have done, so this is done through the info.getMAC address function. The only thing that we have done that was not in the original ECM patch was to add some extension in the GNI layer, so that so this is C code, so actually there is some way done in C for us to fetch the MAC address from the ETH0 interface. So this is not really complicated development, I would say, but at least it's useful for the user, in a user perspective. Then another problem that we had was regarding DNS management. So DHCP was working, but it was not providing any valid DNS entry. So you may ping some IP address, and then you would just try to ping some name server. It doesn't work. So this was a problem. So this was more a problem because it used to work with Wi-Fi and not with Ethernet. And that's how we discovered that there was actually two different kind of implementation of the DHCP. And on Android, as I said, there is no etc result.conf file because everything is done by Bionic C library, and they use some system properties. So the system properties are some, I would say, volatile information in memory under this form, so net.dns1 equal and a value, and this is kind of information and the way that Android stores these informations. So what we had to do was to modify the DHCP scripts so that when the DHCP comes out with the answer from the DHCP server saying, okay, this is my DNS server, then we have to provide them back to the Android framework. So we have done that in two ways. One was in the Java layer. So we just use the system properties functions just to say, okay, just put the net DNS1 and the net.eth0.dns1 properties and say this is the values that we have. And also we have modified this, which is the DHCP C applications. Actually, it's a C daemon that calls shell scripts in order to provide the different system properties. So we just had to add these two lines in order to set the properties right. When we did that, we also discovered that we had some issue with that because we had some permission denied because this implementation of DHCPD is actually used by the netconfig command. So if you log in the shell and do netconfig DHCP, this is the kind of DHCP implementation that is called. But you usually do that only in root, so you have the rights. But in our case, it's the Ethernet manager, which is calling the DHCP, which is trying to set the variables, and this one is running in an unprivileged mode. And this mode is the DHCP ID. So what we have to do is hack the init layer and just saying that all the applications that have the Android ID corresponding to the DHCP are actually allowed to modify the net.something system properties. Then comes the HTTP proxy support. So for the proxy support, I'm in a big company, so I have a proxy, and I just want to put it once and ensure that all my applications actually know how to bypass this proxy. So once again, we have modified some values in the frameworks in order to specify what is the proxy port. And we also had to modify, once again, the connectivity service to declare some new system properties, which is the net.http proxy properties, which is not always known by the system. And this way you just tell the system, okay, I have a proxy and I want my app to know that I have a proxy. Another kind of issue that we had was the NTP server, because we were behind the firewall. So behind the firewall, the default NTP server is actually outside the company, so it's blocked. So what we have done is actually adding some new variable, some new field in the settings applications that allows us to use our personal internal NTP server. So once again, there are examples of the codes of different implementation. We have hacked the framework a bit for the NTP classes in order to be able to, in the settings applications, to input our own IP address for the NTP server and store it in the SQL database so that the application will be able to use the right one. We just have to modify also the network timeout service just to register to the event Ethernet connected, so that every time the Ethernet is plugged in or plugged out, but mostly plugged in, then it just sends some notification to the NTP saying, okay, just try to fetch the time again. So once again, it's different example of codes about the implementation of the NTP server changes. Another issue that we had was about the email. So if you just take the email application of Android, you can read emails through Ethernet with that, but you can't download an email attachment, so it's really stupid. But actually, once again, if you just have a look at the code, you say, okay, if I am connected with Wi-Fi, then I allow that, otherwise it's just denied. So it just, once again, a couple lines changes, but you say, okay, if I'm Wi-Fi or Ethernet, allow to download emails, but natively you just do not support that. Another issue that we have, even the device is not, I would say, officially supported by Google because it doesn't meet the hardware specifications. We just try to support the most applications as possible, and so we just took the Play Store applications from the CyanogenMod distribution, and trying that, we just launched the application and it just crashed. Okay, so it happens with Android sometimes. Okay, let it crash. Try it a second time, still crash. Okay, this is kind of annoying now. So having the application crash is not what we expected. So as it was a proprietary application, this is some kind of side note, but the best way was to reverse engineer the application. So if you want to do that, I can recommend you two excellent tools with our Dex2jar and the Java decompiler. The first one extracts the classes.jar package from your APK file and decrypts it. And the other one is an enlight that allows you to browse, to decompile the Java classes and tries as much as possible to understand what's beneath this proprietary code. So this way we were actually being able to see that many applications, at least this one, consider that Wi-Fi is an application in your device. And we were not supporting Wi-Fi, at least not in a station mode. So all the calls from the applications to the connectivity service saying, hey, is Wi-Fi connected or not? They were just crashing because we do not have Wi-Fi. So once again, what we had to do was to modify the connectivity service, and in the get network info function, instead of just returning the get network info with the regular type, we just hijack the stuff, saying, okay, if some application for any reason asks for mobile or Wi-Fi or WiMAX support, let's just consider that they have asked for Ethernet. And this way, then we can just say, okay, Ethernet, am I connected or not? But at least the application, they just bypass this check. So this is really ugly and tricky, but this is the best way for the application to work and actually not to crash. Another issue that we had was regarding the download provider. So this is kind of funny because, as I said, the browser works out of the box because it's coded in C, C++ using WebKit, works as a charm. Then you just browse on the website, you click on some link that you're interested in and you want to download, doesn't work. Okay, so actually download is not implemented by the browser itself, but by some providers, which is the download provider. And if you have a look at this code, once again, it's only support download over Wi-Fi, or maybe over 3G network, but at least not over Ethernet. So what we have to do was simply to modify the switch case and add some connectivity manager type Ethernet support. And this is a one line, but at least you say, okay, if you're on Ethernet, still allow the download to work. Still on the browser side, this is also interesting. The browser works, the download works now, but we just hit YouTube, it doesn't work. We can't play video. If you take the stage right application in console, it doesn't work either. So we understood that it was not a browser problem. So actually, this is a stage right problem. So stage right is the multimedia layer of Android, and they support two different stacks for actually streaming from HTTP. One is called the Chrome stack, and the other one is the Android stack. So our recommendation was to use the HTTP Chrome stack, and we have hacked this stack in order for the stage right framework to actually get the property nets.http.proxy that we said before and just tell this framework, okay, I have a proxy, so I want your media player stack to actually use this proxy when you're trying to go out. So this is done by these couple lines. And doing that, we see that the HTTP connection was kind of working, but it was still kind of stuck. So we modify once again the connectivity service applications, and this is really tricky. We were using some IMX6 platform from Freescale, and actually doing the strings command on the OpenMax libraries, we managed to see that they were looking for some specific system properties that were obviously undocumented. So these libraries were looking for the net.proxy and the rw.http proxy system properties, which is also one more way to specify a proxy, but it's really Freescale specific. And what we have done is add the connectivity service and add these two lines so that, okay, the OpenMax stacks actually knows about the proxy. For the phone and the SIP voice over IP, there is also the same issues as usual. It's really, there is some settings in the Android framework that's really prevented from working from anything but 3G or Wi-Fi. So we just have to hijack the application once again in order to add the same kind of check. Am I connected behind Wi-Fi or behind Ethernet? We did the same for the network statistics, not that it's really important for the whole data usage because you're not paying an Ethernet plan most of the time, but at least if you want to debug your application, knowing how much packets have been coming out or coming in, this is really important. So these are some examples of the codes that we have modified so that the data tracker actually knows about how much packets and bytes have come through the interface. So what are the next steps of this work? As I said, the ECM patch that we have taken, as its architecture doesn't really match the Wi-Fi architecture. So it works, but it's not really implemented the best way. So one of the steps would be to properly redesign this one, and then the work has been done on Ice Cream Sandwich, and we intend to port it to Jelly Bean. So I don't expect the code, at least from the network side, to change much, but we need to port it to the latest version. We also see that if the ECM patch has changed, we took it, it was like March 2012 when we took it first, so it may have been updated a bit. But even with that, the current change set is some kind of really big patch because it's pretty much half a megabyte big, so kind of a lot of work in there. We also need to design the support for maybe Fox.heaven and HAL, because not that we really need it, but at least it's the way of doing things. So if we want to bring a proper authentication support with WPA, maybe we need to do that. And for the future of this patch, the idea would really be to have it redesigned and well done, and then try to push it back to Google. And the only way I can see for that is trying to push it back to Linaro first, then it may be pushed back to Google. But it's pretty much the only way that SNet can be actually implemented. So this is pretty much all that we have done and all I had to present to you on today. As I said, the patch is not yet publicly available. I haven't created a GitHub repository or anything, but if you guys are interested, you may just send me an email. All the slides will be presented. It will be available on SlideShare, so just drop me some mail, and if you're interested in the patch, I will gladly send it to you, and you can do whatever you want with that. It's fully open source, so just deal with it. Okay. If you have any questions, I don't know if we have too much time. Otherwise, we can do that.